deep learning has demonstrated impressive performance on tasks related to natural images, such as photographs. These techniques are now being applied to medical imaging processing. Techniques include classification, segmentation, and detection, and we'll go over all of them. Classification tasks in radiology consist of predicting some target class at the patient level from an image or region of interest. This task encompasses a wide range of applications, from determining the presence or absence of a disease to identifying the type of malignancy. Using deep learning, these tasks are commonly solved using CNNs, convolutional neural networks. After forward propagation of input images, the softmax layer will produce a vector of class probabilities from which the highest value represents the predicted class. Compared with traditional computer vision and machine learning algorithms, deep learning algorithms are data hungry. One of the main challenges is the scarcity of labeled medical imaging datasets. While millions of natural images can be tagged using crowdsourcing, acquiring accurately labeled medical images is complex and expensive. Furthermore, assembling balanced and representative training datasets can be daunting, given the wide spectrum of pathologic conditions encountered in clinical practice. To manage the scarcity of labeled images, a common strategy is to pre-train a CNN first on a task for which there is a sufficient amount of data available. This technique is called transfer learning. Since models pre-trained on the popular ImageNet challenge dataset are now widely available, many authors have achieved good performances by reusing pre-trained generic architecture and fine-tuning the final layers of the network to fit a relatively small and specialized dataset. In terms of evaluation metrics, the performance of these models is typically assessed using accuracy, the ratio of correctly predicted samples over all predictions. For tasks comprising multiple target classes, it's common to report the top 5 accuracy, a similar metric that assesses whether the correct label belongs to the 5 highest predicted class probabilities. One way to visualize the performance of the neural network is to generate a confusion matrix, reporting predicted and true labels. Here's an example of transfer learning, where a network is initialized using weights derived from training on a large dataset. Only a portion of the network, typically the final fully connected FC layers outlined here, needs to be retrained for a new, smaller dataset. The underlying assumption is that basic image features may be shared among seemingly disparate datasets. The height and width of red boxes, respectively, represent the resolution and number of feature maps resulting from the current layer operation. Next is segmentation. There are 2 deep learning approaches to image segmentation. The first is a patch-based approach where the center pixel of a patch is classified. The whole segmentation map can be obtained by applying the model in a sliding window fashion over the whole image and progressively building the output segmentation mask by segmenting the central pixel of each patch. This simple approach requires many model evaluations to obtain a segmentation map for a single image and thus is computationally inefficient. A second approach is based on a CNN that directly produces full resolution segmentation output. While CNNs typically consist of a contracting path composed of convolutional downsampling and fully connected layers, in this segmentation model, the fully connected layers are replaced by an expanding path, which also recovers the spatial information lost during the downsampling operations. In most cases, the expanding path is built with upsampling operations, responsible for increasing the spatial resolution of feature maps, and skip connections, used to pass the information from the contracting path of the network, bypassing the deeper layers. This architecture is known as the U-net because of its U-shaped architecture, and is currently broadly used in medical image segmentation approaches. In terms of evaluation metrics, pixel-wise classification accuracy is a poor metric for segmentation, since most pixels in an image do not contain the target class. Furthermore, it does not account for the variability in size of different lesions and does not faithfully reflect the segmentation quality. Therefore, most authors report metrics based on the intersection over union of the segmentation mask against a ground truth segmentation mask created by an expert. In the medical field, the DICE score is commonly used as an evaluation metric and takes a value of 0 when both masks do not overlap at all and 1 for perfect overlap. One example application is automated tumor segmentation from CT and MR imaging. Here's the pipeline for lesion segmentation. A particular architecture of CNNs, called the U-net, is designed to output complete segmentation masks from input images. By expanding the max pooling layers with corresponding upsampling layers, the output dimension of the final classification layer matches the dimension of the original input image. Skip connections connect the contracting path left with a path on the right. Last is detection. Detection of focal lesions such as lung nodules, hepatic lesions, and colon polyps are critical skills as a radiologist. While classification tasks aim to predict labels, detection tasks aim to predict the location of potential lesions, often in the form of points, regions, or bounding boxes of interest. From a machine learning perspective, these three types of outputs give rise to three different approaches to detection. It can be viewed as classification, where a predefined set of candidate patches sampled around points of interest are further classified as positive or negative. It can also be considered a segmentation task in which detection becomes implicit, as individual connected areas of the resulting mask are considered detected samples. Lastly, it can be considered a regression task, where the coordinates of bounding boxes outlining target objects are directly inferred from the input image, a technique broadly applied for natural images. When classifying voxels in a volume for detection or segmentation, a common challenge is that the target class tends to have relatively few examples, where the background class tends to be more numerous and more variable. A common strategy to train a CNN for detection in this setting is to generate a surrogate dataset based on small patches extracted from the original images. Patches will typically be sampled in equal number from the target class and the background class, providing a simple mechanism to mitigate the class imbalance naturally occurring in detection tasks. A CNN is then trained on this patch dataset as if it were a classification task. It can subsequently be applied in a sliding window fashion across an input image, or on a subset of pre-selected image patches previously obtained with a sensitive candidate selection method. By casting the detection task as a classification one, pre-trained architectures can again be leveraged to achieve good performances with small datasets. In terms of evaluation metrics, reporting performance on the basis of accuracy is not very informative, since most of the image contains normal tissue, i.e. true negative, which is likely to overshadow missed lesions, false negative. It therefore is common to report a combination of metrics that do not account for true negatives, such as sensitivity, also known as the true positive rate, positive predictive value, also known as precision in computer science, F-score, and average false positive per patient. To explore various operating point trade-offs of this training model, it's common to report, instead of the traditional receiver operating characteristic curves, the free response ROC curves, FROC, which plots the lesion localization ratio against the non-lesion detection ratio for various cutoff points. This is an example of training with patches. Detection tasks in the medical field are commonly solved by training convolutional networks on a surrogate dataset composed of small patches extracted from the original images. For volumetric modalities, different sampling strategies can be used to integrate 3D contextual information, such as using 3D patches or cross-like. Patches are typically sampled in equal number from both classes to mitigate the class imbalance naturally occurring in detection tasks. Just as for classification, the CNN can be pre-trained on an existing database and fine-tuned for the target application. In terms of limitations, there are many. 1. Well-structured data or well-defined features can often use simpler methods, like logistic regression, support vector machines, and random forests. 2. As mentioned, AI is very data-hungry. There's a need for large, labeled, public medical imaging datasets. Fortunately, there are initiatives like the Cancer Imaging Archive to do just that. 3. Radiology can be a black box and can be opaque. This can be difficult for radiologists who may need complex interpretations at times. There are many future directions. The role of deep learning and its application to the practice of radiology is still evolving. Deep learning systems may be conceived as a new form of diagnostic test with various clinical usage scenarios. For example, as a triage approach, one can run AI in the background to detect life-threatening conditions or search through large amounts of clinical, genomic, or imaging data. In terms of a replacement approach, AI can generate figure captions or even fully automate interpretation of certain imaging exams. And lastly, as an add-on approach, it would support the radiologist for performing time-consuming tasks such as lesion segmentation to assess total tumor burden. You now know a lot about artificial intelligence and radiology. Please subscribe for more awesome anatomy and radiology videos.